Okay, so now we will study the quantum counting algorithm, which can count the number of solutions in a quantum algorithm in a search database before applying the Grover search algorithm. We actually saw this when we were studying Grover algorithm, that we need to know the number of iterations R that we have to apply on the number of, the number of times we have to use the oracle and the diffuser beforehand, before we are, able to use the Grover algorithm. So there was, of course, the need to know the number of solutions present in the search space before we can apply the algorithm, because R depends on that. So that's what we are going to do now, which we can easily accomplish using quantum phase estimation algorithm. So let me show you how, and for that, let me share my screen. Okay, so quantum counting algorithm is actually uh, just quantum phase estimation. The only difference is now that our unitary operator is the Grover operator, which is actually equal to the Grover oracle U, let's call it UF, and the diffuser V. So if you remember from the algorithm, Grover algorithm, it worked like this. We had a search space, we had an algorithm that started in zero state, and then we applied a Hadamard transform to transform into a state S, which was the, a superposition state of all possible combinations. And then we applied the Grover oracle. And then we had this diffuser V, and then measurements. But this part has to be applied R times. And this diffuser V, if you recall, this was Hadamard tensor 0 minus 2i tensor Hadamard. And this part, so, and this was the oracle that, marked the solutions. So this has this property that f of x was 1 if x, is equal to w, and this is 0 if x is not equal to w, where w is our solution. And so in general, we wrote this oracle uf as identity minus 2w. So it gives a minus sign to w. And this was the oracle that marked every input combination other than 0, 0. So that's why this was 0, 0 minus 2i. Okay, so let's call all of this an operator G, and we will shortly see that this is a unitary operator. Actually, it's a combination of unitary operators, so it has to be a unitary operator. But we can see it in this way as well, that the state of the system over here is S. And if you recall from the Grover algorithm, we were able to write it as cosine of some angle into W perpendicular plus sine of some angle into W. where actually I have changed notations little bit. So last time we were calling this theta by 2 as alpha. But a lot of quantum algorithm books, they call this theta by 2. So let's use this notation theta by 2. So graphically, you can visualize this state S as having an angle theta by 2 with omega perpendicular axis and 90 minus theta by 2 with the other axis. And to also recall, the job of this U, F, and V in combination was to take this vector S from here to a position where an angle theta is added into it. There's an intermediate step which I'm not showing this time. So when UF is applied, this actually goes to this position, and then when V is applied, it goes from here to here. But the overall job of this operator UFV, actually VUF, is to transform this vector S from an angle theta by 2 to an angle theta plus theta by 2. So it means that I can describe the action of this Grover operator as this, that the angle increases by theta like this. So this G is essentially a rotation operator because it rotates the state S from here to here by an angle theta. So I can also express this action like this. So we can express actually this state S as something that has angle cosine theta by 2, angle theta by 2, and components cos theta by 2, sine theta by 2 along this horizontal and vertical axis. And this G is just this rotation operator by angle theta. And you can actually verify very easily that the action of this matrix, this rotation matrix, and this unit vector cos theta by 2, sine theta by 2 will give us cos theta plus theta by 2 and sine theta plus theta by 2. So this unit, this operator G is a rotation operator. And since it preserves the norm of the vector that it applies, and we can also see that it's, transposes its own inverse as well. So this is actually a unitary operator. So let's now see what are the eigenvalues and eigenvectors of this operator, this matrix G. And you can, do it formally by starting with an unknown x1, x2, and solving for these eigenvalues, lambdas, and finding these x1, x2. But at the end, you will see that we have two eigenvectors. So one is iota 1 and the other is minus iota 1. And this has eigenvalue exponential iota theta, and this has eigenvalue exponential minus iota theta. And this, by the way, can also be written as exponential iota 2 pi minus theta. So it means we have two eigenvectors. So this one and this one. And if we can prepare our state either in this or this eigenvector, we can, find the corresponding eigenvalues. Or we can notice another thing. This state S can be written as a linear combination of these two eigenvectors. And let's see how. So this S state, cos theta by 2, sine theta by 2, can be written as cos theta by 2 iota 1 plus sine theta by 2. Actually, let's start with unknown A and B, and let's try to find AB. So A iota minus B iota should be cos theta by 2, and A plus B should be sine theta by 2. Which means that if I multiply with iota here, iota here, iota here, and add them, these cancels out. So I'm left with 2A iota is equal to cos theta by 2 iota sine theta by 2, which is cos theta by 2 plus iota sine theta by 2 is exponential iota theta by 2. So my A is 1 over 2 iota E iota theta by 2. For B, I can subtract. So if I subtract, then A's will cancel and I will get minus 2B iota cos theta by 2 minus iota sine theta by 2, which is exponential minus iota theta by 2. So B is minus 1 over 2 iota exponential minus iota theta by 2. So it means I can express my S state as 1 over 2 iota minus 1. So this, is good because I can easily prepare this S state. I don't have to prepare my state in either this or that eigenvector. All I can do is directly prepare my state in S by simply a Hadamard. Because if I start from 0 and I apply Hadamard, I can get this S state. So I can now use quantum phase estimation algorithm by preparing my state in S state and then applying the quantum counting algorithm, because it will then give me both of the eigenvalues corresponding to this eigenvector and this eigenvector. At the end, I will get 2 bars. So one will have height equal to mod square this, and one will have height equal to mod square this. But since they both have equal magnitude, both of my histograms will have equal height, but their position will give me this eigenvalue theta by 2. So where the eigenvalues I've written? Okay, so this will give me this eigenvalue theta, and the other one will give me eigenvalue minus theta. So all I'm interested in theta, because once I know theta, from theta, because theta is related to the number of solutions like this. If you let me just recall that also quickly. I think we defined sine theta by 2 as 1 over n square root, right? And when we had more than one solution, it was mu over n square root, which means that number of solution mu are n sine square theta by 2, where this n is total number of solutions. So if I'm using, small n is equal to 3, then capital N is equal to 2 power 3, 8. These are total number of solutions. And from these total number of solutions, I can find these number of solution mu by using this expression. Okay, any question so far?
Sir,
Mm-hmm.
capital N is total number of solution or total search space?
Sorry, capital N is the number of choices available in the search space. You're right. All right. So let's know.
Sir, how did we take out theta by 2?
How did we take out theta by 2? Where?
From the histogram.
Oh, so from histogram, I will not find theta by 2. I will find eigenvalue multiplied the phase multi. So this index will give me 2 power c multiplied by the phase of the eigenvalue. And so this is, so in over here, I will actually be able to get the phase. So this is the eigenvalue and this is the phase. So I will actually get this direct, actually to be more precise, we had worked out our ways like this with 2 pi here. So I can add 2 pi and 2 pi here and 2 pi here. So this is a part that I will get along with 2 power c over here. So this is this index will give me this quantity, and similarly the other index will give me 2 pi minus theta part. Okay.
Okay, sir.
Sir,
Mhm.
do we need to normalize the state, the superposition state, before setting is at as our initial state?
Which superposition state?
Suppose we are starting our problem in a superposition state of eigenvectors. So do we
Okay.
need a normalized state, or any superposition will work?
Sorry, which state?
This S state is written in the superposition of the eigenvectors.
So,
So
normalize, I don't
not
understand.
normalize.
Normalize. It doesn't
Do we
matter.
need to-
So all states that we are, starting with, we are taking them to be normalized. So whenever you will prepare a faithful state on a quantum computer, they will all be normalized.
Okay.
Yeah. And okay. So any other question? So let's just see what this index of the second histogram will tell us. So one eigenvalue is exponential. Where are the eigenvalues? So this is exponential iota theta. The other is minus iota theta, which is just exponential 2 pi minus iota theta. And this thing, exponential iota 2 pi minus theta, is exponential iota 2 pi 1 minus theta over 2 pi. So we will actually get this divided by 2 pi. So over here we will have 2c 1 minus theta over 2 pi. So this is what we will, the index of the second will tell us. Okay, so it means that this can be transformed. So theta is going to be 2 pi into measured integer divided by 2c. And over here, we will have 1 minus theta over 2 pi measured integer divided by 2c. And I can take this there and this here. And then 1 minus measured integer 2c, 2 pi, or this is equal to. So this is how, we can get both. So you can use, either one to find this theta. But the important thing is that once we know theta, we will know mu immediately. But there is one catch that we need to remember, that the algorithm assumes so far that we have implemented our diffuser with this, oracle. But if you remember correctly, instead, so this means that we have this one and then -1, and so on. But this means that we have to prepare an oracle that gives a minus sign for each of the other input combination other than 0, 0, 0. So since this just introduces a global phase, if I take minus common, so one way to do is that we take a minus here and just give a minus sign to this one. So if we, we have implemented diffuser with this thing, okay, instead of giving, if instead of doing it the other way. So that means that our solutions are being marked in the opposite way. That the effect of this UF is that it doesn't mark solution, it marks everything other than solution because of this minus sign appearing here. If this minus sign goes to UF, so UF was doing 1 1 1 and just marking once some of the solutions and keeping everything else positive. But if this minus sign is coming, it means these two are becoming positive, which are solution effectively, and everything else is becoming negative. So at the end, when we find this mu here, this is not going to be number of solutions, but this is going to be number of n minus solutions. So solutions are actually going to be total minus mu because of the negative sign over there. But anyway, despite this catch, the algorithm is still very simple, and let me sketch it. So the algorithm works like this. We have C number of counting qubits starting in 0, applying Hadamard, and then using these qubits as control qubits for applying controlled unitary operation. But I have to prepare my state S. So let's say these are n qubit. So I start from 0 and apply another Hadamard here also. So now, this gives me state S, which is the superposition of all eigenvectors. So now I can apply this Grover and then controlled by the second Grover square. And then by the next qubit, Grover power 4, which is 2 power 2, and so on. So all the way to Grover 2 power C minus 1. And then applying an inverse quantum Fourier transform here and doing measurements over here. So this is how we can use it. Now the next question is that how do we, perform this Grover operator again and again? So how do I perform Grover square, Grover 4, and so on? So maybe by using, the combination of U and F, you can design some clever ways. But I'm going to implement these, Grover powers by just repeated application of Grovers. So this Grover 4 for me is just Grover 4 times, controlled by, this qubit. Similarly, Grover square is 2 Grovers. And you can also prepare a combination, this Grover as, a single operator, but I'm actually going to apply it as, 2 independent operators. Sorry, I'm still writing it in the opposite way. So UF, because UF will apply first and then V. So I will actually be using this Devian when I implement it in Qiskit. And let me show you an implementation. So let's start to go through the second notebooks. Okay, so I first present an algorithm that is implemented for a single solution in such space. So I begin with, usual imports. And then, this is the part of the circuit that marks single solution, a solution 1 1 1. We can already see, because when all this Q0, Q1, Q2 are 1 1 1, the solution will be marked as negative with a minus, minus phase. You see this Q3, I'm just, recalling, this was a qubit, which is auxiliary qubit set in 0 state. And this Q4 is the qubit that we had to set in minus state, because this is ultimately the one that we will be using. So now I'm implementing it as a function in phase oracle, because this is something that I will be calling later on. So let's use this. And then this is the UF part, because this always marks this is a part of the diffuser, because this marks the 000 index. When this is 000, this will give a negative phase, and this is Q3 still an auxiliary qubit. So this is done, and now you see that I can construct a diffuser by having Hadamard's, and then these X gates, and then these 3 Toffoli gates, and then X gates, and then a series of Hadamard, and I'm enclosing it in a function, and I'm giving it some name V. Do we have name for this one as well? Phase oracle? No. Okay, so let's now prepare this, Grover algorithm, this Grover circuit, but I'm not going to use this, so let me just not worry about it. Now I have to use this, phase and diffuser again and again. So I'm going to convert them to a gate, and the scheme to convert a circuit to a gate is given here. You have this phase oracle, and you can use this extension .to gate. So it is converted to this U gate. And I'm adding this label GR phase to this gate. Wherever this gate will be used, this will have this, name GR phase, Grover phase. And then I'm converting it into a control gate. So you can do that by this command .control. So Qiskit can do it for you. So now this, this phase oracle has been converted to a control gate. So once I use this, I can now use this con U symbol and use it as a control gate. So this will be a controlled phase gate, phase operator. Similarly, I can convert this diffuser circuit into a gate by applying this .to gate extension, and I now have, a way to call my diffuser and Grover phase. Okay, let's start with 4 counting qubits. And even though n is equal to 5 written here, so essentially n is 3. And the reason is that 2 are the auxiliary qubits. So only 3 qubits are used, for solutions and for database. Okay, so you see that I have applied the Hadamard and everything except for the last 2 qubit. And the last qubit is put in the in the negative state, and the second last qubit is not touched. And then I'm using the same scheme as in the quantum phase estimation. I'm preparing this exponent 2 power c minus x minus 1, and then I'm applying exponent number of times my control U gate and my control V gate. Now, the way to specify control qubits and the target qubits is written here. So this first one is the control qubit, which is, coming through this J, this X, and then this is, C2n plus C are the target qubits, because this is, a 3 qubit, a 5 qubit circuit that will be implemented on the last n qubits. And then I have this, inverse quantum Fourier transform on the counting qubits only, and then at the end I have this measurement. So actually, to show it to you, let me start with the C is equal to 3. So here is the circuit, as you see. So Grover phase and Grover diffuser. So this makes one Grover, then Grover phase diffuser makes it another Grover, and so this is Grover 4 times. So these, first 4 boxes are Grover power 4. So this is G power 4. And then there is 1, 2, 3, and 4 boxes are Grover square, because this phase and diffuser makes up one Grover, and then phase and diffuser makes another Grover. And the last one is a single Grover. And you can see they are being controlled in an opposite way, as I described in the lecture notes, simply because Qiskit handles them in the opposite way. And then Q6 is kept in the 0 state throughout. This is the ancilia qubit, and Q7 has been kept in this minus state to give the phase. All right, so let's now run this circuit. And now you can see that since I have used 3 Hadamard here to prepare my X state from this 0 state, in the output, I should have, 2 bars, one for each of the eigenvectors. And from this counts, I can still get this highest probability string, which is going to be either of these. And I have converted it into integer, so that value is placed in Meyer integer. And here you can see that I am first computing this capital N, which in this case is n minus 2, because here n small n is being used for all of these 5 qubits. But even though practically the n is only 3, because the 3 qubits are being used for this Grover operator. So n is 3, and to make up for that 3, I'm putting n minus 2 here. And then I'm computing theta, so which is 2 pi. So I'm calling this another package math as MT. You can also use numpy if you like. So 2 pi into Meyer integer divided by 2 power c. And once I have that, I compute the number of solution m as n times sine theta by 2 square, and I'm printing m, n, and n minus n. You can see that m is 6.8, capital N is 8, so number of solutions are 1.17. And we have used a situation with only single solution. So this marks a single solution. So any question about this quantum phase estimation circuit? Let me also show you a situation where I have prepared an oracle that has 2 solutions. So let's start with this thing. So this is an oracle that marks 2 solutions, and you can easily see, because when this Q0 and Q1 are 1, 1, this Q2 can be either 0 or 1, and you will still get a phase over here. Right? Because there's no control on K2. So whenever Q0 and Q1 are 1, 1, we will get a phase. And Q2 can be either 0. So one solution is 1, 1, 0. The other solution is 1, 1, 1. So this oracle implements 2 solutions. So let's see if we get, you can see I'm getting close to 2 solution, 1.77. We can actually make the accuracy of solutions a bit better by, let's say, increasing C to 6. It's gonna take a long time now to run because our circuit is huge now. You can see it's a big circuit because C is 6. So now it's like 2.11. So you can increase the accuracy of solution by increasing the number of counting qubits. Okay, so any question so far on quantum counting algorithm? Okay, so this then concludes this quantum counting algorithm.